First thing, we need to look at the purpose for doing such a thing. Well, the purpose, in this case, is to actually find the gradient. And it's the gradient of a curve. For instance, take the function y is equal to x squared plus 1. If you look at a function like that, it generally has this shape. Now, we know we find the gradient by finding the tangent at a point. So we just pick any sort of point here, we can find the tangent there. But that tangent obviously varies depending on which point we're actually choosing. So it's different at all these points, it will vary. So it would be nice if we could just find a general rule which tells us the gradient. Now to find this rule, we need to remember that our gradient is the change in y divided by the change in x. Well, if we have a look at our tangents again, have a look at our curve. Now if we just take any point x, it has a corresponding point y. Now if we want to find our gradient, we go a little bit further on. We take this distance here as delta x, a little bit more. This point becomes x plus delta x. So from that point, we have a new point y. So that's y plus delta y there. Now, what would be the best is if this distance here, delta x, was as close as possible to 0. That would give us the best estimation for our tangent. So we say this derivative, dy dx, is equal to the limit of delta y divided by delta x as delta x approaches 0. Let's take a specific example here. So first of all, I'll clean this board. Let's look at this function, y equals x squared plus 1. What we want to try and do is find the gradient at any point along there. So we've got a function that tells us the gradient. Remember, the gradient is the change in y divided by the change in x. Well, let's just start with some x1 value, and let's let it equal x. There's our x1 value. Now, y1 corresponds over here, here's y1, it equals x squared plus 1, because it's just that function, we just substitute straight into here. We need a second point because we're finding a gradient. Let's make this x2. Now x2 is going to be a little bit more there. I'm going to take that value as delta x. That little bit more is my delta x. A little bit more. So x2 is equal to x plus delta x. That little bit more. So y2 is equal to x plus delta x all squared plus 1. We need to expand that out. So this becomes x squared plus 2x delta x plus delta x squared plus 1. There's y2. Now let's go back to what we're trying to do. We're trying to find the gradient. We find the gradient by finding the change in y, the change in x. So let's do that. Change in y equals y2 minus y1. y2 is equal to x squared plus 2x delta x plus delta x squared plus 1. That y1 was equal to x squared plus 1. Subtract these two, so the x's cancel, x squareds cancel, sorry, and the 1's cancel. So delta y is equal to 2x delta x plus delta x squared. But remember, we wanted not just to find the gradient, we wanted to find an equation for the gradient. We call that equation dy of dx, the derivative. So dy of dx is equal to the limit of delta y over delta x as delta x approaches 0. Well, let's have a closer look at that idea. Well, we've got dy over dx, sorry, I've got the dy over dx down here. Dy over dx equals the limit of delta y, which we found this to be delta y, 2x delta x plus delta x squared, you still see that, divided by delta x, as delta x approaches 0. Well, we take out a common factor. Delta x will be a common factor, so it's the limit of delta x outside of 2x plus delta x divided by delta x as delta x approaches 0. But you can see delta x will divide into delta x once. So you're left with the limit of 2x plus delta x as delta x approaches 0. So that means if this is 0, we substitute the 0 in for the delta x there. So this is equal to 2x plus 0, which is equal to 2x. So our derivative, dy on dx, is equal to 2x. So at any point, we can find the gradient. So for instance, if x is equal to 3, then m will equal 2 times 3, which equals 6. Thanks for paying attention.